Welcome to another lecture of data formats. Today we are going to talk about hierarchical data formats, and more specifically we are going to talk about XML and XML schema. We'll start with XML, which is a data format for hierarchical data models. I will approach the introduction to XML from two different angles today, and this is the first one. So let's say we have a human readable message like this. It's a letter which says something about a bank account and a date and the balance on that bank account. And this is obviously a human readable message. So the goal, as always, will be to make it more machine readable. So what we can do, we can point out those pieces of the human readable message which contain the data, which contain the machine readable or machine processable pieces of information. Like this. We will denote the name of the person, the account number, the balance date and the balance, and then the address of the bank and the phone number and so on. So the important pieces of data will be delimited using these kinds of tags, and we will call them tags, and we will name them so that it is clear what the data in that place actually represents. So we know that in the beginning there is a customer, then there is an account number, and so on. So this is a first step towards machine readability, because the machine doesn't have to guess what some of the numbers mean. We tell it what those numbers or dates actually mean. So this is like a first step in making this document more machine processable. And of course we would need some more detail. So we may actually want to split the customer name to first name, last name, and the balance we want to split into the value and the currency. The advantage of actually tagging the document in this way is that when we remove all the tags, the document still remains human readable. So if we were just to remove all the tags, the document will still be human readable. You would see it as a normal letter, and this is easily done using code. So actually, this document can be both human readable and machine readable. And to make it actually valid XML document, we would have to introduce something called a prologue, which is the first line, and then we would have to enclose the whole message in one root element called message. So this is a complete and valid XML document, and this is called document-centric or document-oriented XML, because it is an XML file, which, however, is still a human-readable document. And as such, it has some properties. For instance, it is clear that this one was created manually and then tagged. It's structured irregularly, so it is not a set of records which all look the same. It is still human readable, and if you know HTML, you can see that this is similar to HTML, and this is no coincidence, because HTML is a tagging language introduced for better formatting of text files, documents. There is also an implementation of HTML which is actually an XML file, and that one is XHTML, which takes the HTML tags and applies the stricter XML rules, which we will talk about in a moment. So this is a document-centric or document-oriented XML. And because we are talking mainly about data and not documents, this is the second angle of introduction to XML. This image is something that we have already seen. It's the conceptual model of a data catalog. And we talked about how to represent the data modeled here in RDF in quite a natural and straightforward way. Well, for XML, representing this data in XML is not so straightforward because the conceptual model is a graph and the XML file is hierarchical, so it is a tree, which is a graph, which is oriented, but it has a root, and the edges go only in one way, from the root down, and there cannot be cycles. So XML is more restrictive, and therefore we need to do some operations and think more about how to actually represent the data modeled this way in XML. So the simplest way we can do this is that we pick a correct root for this data if we assume that the data can be represented as a hierarchy. For instance, we can select the data catalog here as a root, and we so-called hang the data from this catalog class. So you can imagine this as picking the catalog class and hanging the rest of the diagram in the shape of a tree. So this would mean, of course, orienting all the edges, but for lots of data this is actually doable, and this is how it is typically done. Of course, then you come into situations where this cannot simply be done, and then you are left with basically splitting the data into multiple XML files or devising some pointer techniques so that you can point from a leaf of an XML tree to some other element to simulate the backwards edges, which are not possible in XML. Right, so when we do this, the resulting XML can look like this. It is an XML file, it has a prologue, a root element which represents the catalog. We chose the catalog because when looking at it as people, we decided that this will be the most appropriate root for the hierarchical data. And then we follow the edges and the attributes. So we add the title, description, and contact point, for instance, and then we use the XML nesting, the hierarchical structure of XML, to actually nest the connected instances of connected classes. So here we have the catalog. In the catalog you can see the contact point, and then you have a datasets element containing all the connected datasets to this catalog. Of course, here you can see that, for instance, the dataset edge in the conceptual model has the 0 to many multiplicity at the catalog association end, which means that one dataset can actually belong to many data catalogs, which would be hard to represent here. We would have to have another XML file representing another catalog, and in that catalog we would have to have the same dataset represented all over again if we were to say that one particular dataset belongs to many catalogs. So this is why the selection of the root element is so important, because it captures the most common use case, basically, which is that you have a catalog full of datasets and you leave the case where the dataset actually belongs to multiple catalogs to be solved with redundancies. Right, so if we end up with a XML file in this way, this is what we call a data-centric or data-oriented XML. It is a bit different from the document-centric XML because when we omit all the tags, the document is no longer human readable, and those files are actually typically created by exporting a relational database or created directly in an application. They are structured regularly, so you can see that there are records, repeated records of datasets, repeated records of catalogs, and so on. And typically, the data-centric XML does not contain mixed content. We will talk about mixed content again in a bit, but it is the case where in one element you are mixing both text and other XML elements. Right, so those are two angles of how you can end up with an XML file. Either by tagging a human readable document or by actually directly creating the XML file, either by exporting from another data format or by directly creating the data, for instance, in an application. Which brings us to the overview of specifications which define XML. So as you can see, there are again multiple specifications talking about XML. Mainly, there is XML version 1.0 and 1.1. The main difference between those two lies in the usage of Unicode within element names and namespaces and so on. And actually, both the XML 1.0 and 1.1 went through some kind of evolution, and how it ended up, you can see in the overview. Because first there was naturally XML 1.0, which had a limited usage of Unicode, so XML 1.1 was created, where Unicode could be used quite freely. And there was a principal difference in approaches. While XML 1.0 listed permitted characters, therefore, when Unicode evolved, the newly added characters were not in the list of permitted characters and therefore couldn't be used with XML 1.0. In XML 1.1, there was a list of forbidden characters, and therefore, when Unicode evolved, all the newly added characters were not on the list of forbidden characters and therefore could be used. However, since XML parsers, which implemented the 1.0 version, would break when presented with a 1.1 version document, those two versions actually coexisted in parallel. And eventually, the creators of those specifications found a way of actually relaxing the XML 1.0 restrictions so that most of what was proposed for XML 1.1 could be done within XML 1.0. So there was a fifth edition created in 2008, which incorporates some of the advantages of XML 1.1 regarding Unicode usage. Nevertheless, even today, XML 1.1 is not actually widely used. What this means is, for instance, if you try to open an XML 1.1 file in Firefox, and web browsers typically open XML documents, what you will end up here with is a strange error with no text, which is not up to the specification, because the XML specification says that when an XML 1.0 processor encounters a document which is, for instance, 1.1, it should process it as 1.0. And this document that I created is actually a 1.0 document, only the version in the prologue is 1.1, so there should be no problem. But still, simply by indicating the version 1.1, the processing of the file breaks. And this is unfortunately the case for many XML implementations, even though there is nothing wrong with the XML 1.1 specification. Right, so this was a bit of an overview of the main versions of XML out there, and from now on we'll focus on what actually XML contains. So here we have an example of an XML document. So it is a hierarchical data format, as I already mentioned, and let's describe what we can see here. So first of all, there is a prologue, which is also called an XML declaration. The declaration contains the XML version. The reason for this is what I just talked about. And then the encoding. Nowadays, you should only see UTF-8 there. However, and especially in the Czech context, in legacy systems, you might come across ISO 8859-2 and Windows 1250, and sometimes even UTF-16. Nevertheless, when you create your files and you work with XML, use UTF-8 as in any other modern data format. One remark, the identifier of the encoding is case insensitive, so you might come across UTF-8 using capital letters, like in this case, but also lowercase, and both are fine. Then the entire XML document consists mainly of tags. There is a start tag and end tag to each XML element. So the element, when we talk about XML element, we talk about the start tag, the end tag, and the content, which is what is between those two tags. Those tags are case sensitive, so it does matter whether the characters there are uppercase or lowercase. There is a rule saying that XML document can have only one root element. Now, some elements do not have any content, and for that you can use a syntactic shortcut which looks like this. There is a slash at the end of the start tag, which means it's an empty element tag, which doesn't require any specific end tag after that. And it says the element starts and ends at the same time here and has no content. And then elements can have attributes. And the attributes are written inside the start tag of the element, and they are key value pairs. Each element has a set of attributes. The attributes need to be named uniquely, and they are unordered. So it doesn't matter whether attribute 1 goes first or second. And the attribute names are also case sensitive. Then a key feature of XML is nesting of XML elements, where one element can be nested within another element. The element content is actually ordered. So in this case, for instance, there are two elements, but we know which one is first and which one is second, because the sequence of elements in the element content is ordered. Finally, the green text is comments. So comments in XML can be multi-line, and they start with the symbols you can see in the slide, and they end again with the symbol dash dash and greater than, as you can see. Now, a note on mixed content. I already mentioned it, but here we define it explicitly. So mixed content is a element content which contains both text and elements. The important thing here is that it is still a sequence. In this case, it's a sequence of text nodes and element nodes mixed together. But it is a sequence, so it is ordered, and we know which part of text goes before which element, and so on. Now let's take a look at some basic syntax errors in XML documents which might happen. So the first one is a case mismatch. So I mentioned that element names are case sensitive, so you cannot start an element with element B uppercase and end it with an element B lowercase end tag. Another common mistake is that element D here is started with a start tag, but it doesn't have an end tag. So actually all the other elements here would be inside of element D in its content, and the document would not end, which is of course an error, and each element needs to be either empty or it has to have a start tag and end tag. Another common mistake is a nesting mistake. When you start one element and in its content you start another element. For instance, here the element F is the inner element, and then you try to end the outer element first before the inner element. So this is of course an error. And also an error is that you have multiple root elements. In XML documents you can have only one root element. If you comply, or if your document or file complies with all those syntax rules, you say that the XML document is well formed. You can only come across checking of well-formatedness, which is basically checking of XML syntax of an XML document. So this is it. This is XML. We will have some extensions, but the basics are there. And now you should be able to write syntactically correct XML documents. So now let's talk about some extensions. One of those extensions are so-called XML namespaces, which are quite important in many XML implementations, so we need to talk about those. The problem that XML namespaces want to solve is illustrated here. You can have an element called table, and as it often is, one word can mean many things. In this case, a table can be like an HTML table, like a list of rows and columns, but also a table can be a piece of furniture. Now, if we want to mix in one XML document information about, let's say, HTML tables and tables as pieces of furniture, it would be unfortunate to call both a table the same element name, because then we would not be able to distinguish those, for instance, when we would talk about schemas later, which would tell us what elements can be nested where and what attributes they can have and so on. So for these cases, and these are quite common actually, that we are mixing elements that look the same, or they are named the same, but they mean different things in different contexts in one document. This is quite common. So for that, we need XML namespaces. We will basically split the or encompass the elements in namespaces, which we will identify by a namespace prefix in scope of the document. So here we have two namespaces. We have a namespace prefixed h, or named h, which will contain all the XML element names regarding the table as an HTML table. And then we'll have a namespace called f, or denoted f, and this namespace will contain all the element names regarding furniture. So from now on, if we see something like this, so a string, then a colon, and then a name in a start and end tag, we'll know that this is actually an element name within a namespace. And we do this so that we can clearly identify what each element means. And for that, it is not enough that we denote the namespace using a name like H or F. We need something more global. And we know identifiers which are global, and those are URIs and IRIs. So actually, XML namespaces are identified by their URIs, and then those URIs are named in the scope of a certain XML element, and from the point where they are defined, they can be used to say that those element names belong to this namespace. There is also a term qualified name or QName connected to this, because when we have an XML document like this, actually the table element from now on has a qualified name, which is a pair, IRI of the namespace and the name of the element. And that is why the H table is a different element than the F table, because the H table is a pair which contains the H XML namespace IRI and the table element name, and the F table is a pair which contains the F namespace IRI and the table local name. So those two table elements from now on are clearly distinguishable using the qualified name. And again, a qualified name is a pair namespace IRI and the element name. Now, one side note here, the qualified names may remind you of prefixes in RDF. They are similar, but they are not the same, because prefixes worked in a way where you named a piece of a URI, which might look the same as here, for instance. But then when you used that prefix, the way you got the final URI identifying an RDF resource would be that you take the prefix and you concatenate it with the local name where the prefix is used, and you would end up with an IRI which would identify the thing you are talking about. Qualified names are pairs, a full IRI of the namespace and the local name of the element. There is no concatenation going on, so qualified name is a pair, while prefixes in RDF work with concatenation and end up with just an IRI, not a pair IRI and a local name. So there is a slight difference. Now, I mentioned that the namespace definitions apply to the element where they are defined and the whole content, and therefore you might also want to, for aesthetical reasons, define all namespaces in the root element, and then they apply for the whole XML tree. This is also possible, and actually it means the same thing as in the slide before, where you only define the namespaces locally. So actually this and this is the same. Now for files which contain elements only from one namespace, it might be handy to say that we will not distinguish those namespaces with the string and the colon, and we'll have just plain element names, but we'll say that all the elements in this document belong to one particular namespace. And that is done using the XML NS attribute without any namespace name, and therefore it looks like this. This says that the whole XML document belongs or uses elements which belong to this one namespace. Just note that this is still different from an XML element which would have no namespace defined whatsoever, because elements are identified by their Q names, and Q name is a pair IRI of the namespace and the local name of the element. Therefore, in this case, even though there is no namespace defined explicitly, those are still elements identified by Q names, whereas when we would omit the XML NS attribute whatsoever, those would be actually elements with no namespace defined. So there is a difference. Now, another extension we will talk about is that you might want to use sometimes this CData, character data section. And the syntax is what you can see in the slide, and it basically means that the inside of the CData section is treated as a string, and it might contain all the special characters that a normal text content could not have. So, for instance, here, if you want to embed an XML piece of data as a text and not as a part of the XML document, you can do it like this using the CData section. And then the inside is treated as a regular string. Since XML is used in message exchange, it is again important to specify, for instance, in which natural language a specific text is represented. This is the same as in RDF. And in XML, there is a special attribute called XML:lang. So it is an XML namespace attribute, but the XML namespace is included in each XML document by default, so it doesn't have to be defined explicitly. You can just use it right away. So in this case, XML:lang attribute specifies the natural language of the text inside that XML subtree. The language codes here are the same as in RDF, and HTTP headers and so on. So they are governed by the IETF BCP 47 specification. Another thing you might come across is an XML processing instruction. This one is a bit special because it is to be processed by the XML by the application reading the XML document and not by the XML parser itself, which means that it is actually not part of the XML data of the processing instruction. It just says that any application reading this XML document can do something. For instance, here, the processing instruction targets an XML style sheet processor. We'll talk about XML style sheets in the next lecture. And it says, or links to the style sheet which can be applied to transform this XML document. However, this whole declaration or processing instruction is not part of the data inside the XML document. One more note, you might think that this processing instruction looks a lot like the prologue of an XML document. However, those are by specification two different things. So a prologue is not a processing instruction. Right, another things we need to talk about are XML entities, and we'll just go through the most common ones. For instance, entities used to escape special characters. So in XML, quite naturally, the lesser than and greater than are reserved characters because they denote the start and end tags of XML elements. Therefore, if we want to use those as text, you need to escape those. And escaping in XML can happen in two different ways. One is the usage of predefined XML entities. So for lesser than, you'll use ampersand, LT, and semicolon. Greater than is ampersand, GT, and semicolon, and so on. And you will use those directly in the XML document, as you can see in the example on the right side of the slide. Or another way of escaping those characters are so-called character references, which are seen in the second example in the slide, and they have the form of an ampersand, then a hash, and then either a decimal or hexadecimal number of the character being replaced, and then again a semicolon. And there are some additional constructs of XML which we won't talk about in detail or at all. One of them is DTD, document type definition, which is kind of an XML schema language, which is very simple. It is the first one that was invented for XML, and you can see the example on the left side of the slide. It basically defines the possible elements and attributes, kind of like grammar, using something like regular expressions. Right, if a document has a DTD associated, you can tell it by looking at the prologue of the XML file, where you have also the doc type specification, which looks like the example in the bottom of the slide, linking to the DTD file. And that's all I'm going to say about DTD. And then XML entities, we have seen some predefined XML entities, and you can define your own within DTD to be used in your XML documents. But again, we won't go into that detail. So this covers more or less the XML syntax. Now let's take a look at where we can apply the XML with advantage, and where it is not so good idea to apply XML. One of the cases where it is not so good idea is using XML for tabular data. So what we see here in the slide is basically a table. There is a name, age, and how many coffees per day this person drinks, and that's it. So typically you would represent this data as tabular data. So for instance, a CSV file. Again, we will talk about CSV files in some other lecture, but it is clearly a tabular data set because clearly you have rows and columns, and that's it. However, it can be, of course, represented in an XML file, like what you can see on the left. So here we'll have the table root element, and then we'll have an element for a row and then an element for table header and table data, which are the columns. So it can be done, but the problem with it is that it is kind of an overkill, because for simple data which has tabular structure, you do not use any advantages what XML offers to you. You do not use the hierarchical nature of XML here, because it's just flat table represented using a hierarchical data format. What's worse here is that actually the XML file here resembles HTML, because in HTML, the goal of HTML is formatting the text so that it can be displayed or printed nicely so that it can be read by humans. But in XML, we aim for machine processing and machine understanding of the data. And in this case, it wouldn't work so well, because if you take a look at the XML on the left, what do you think the data is about? Well, given the element names, the data is about a table and about rows and columns in that table, which is actually not what the data is about from the point of view of the conceptual diagram, for instance, that you could create for this kind of data. So the first thing we would like to do is not to denote some syntax or some data structure using the XML elements, but we want to actually denote the data itself. So the first step we could do is stop calling in XML the data, or stop naming it as a table and table row and table cell, and start naming it by the things they represent. So actually the table is a set of consumers, and there is a consumer who has a name, age, and number of coffees per day. So this is obviously better usage of XML, because it at least when we take a look at this XML, we see what the data is about. It's about consumers with names, ages, and coffees per day. It is not relevant that the data used to be a table, right? So this is better, but it is just one step better, because still it is tabular shaped data. It doesn't use the XML's hierarchical nature, and what you did here, basically, if you did this, is that you forced the consumers of your data to use much stronger and much more complex tools to process the data than necessary. Because processing a simple CSV file with 3 columns is much easier than actually parsing an XML document. So let's take the data one step further. Now we'll want to say that the consumers actually drink different kinds of coffee in different times of day. And here the usage of XML actually starts making sense. Why is that? Well, let's take a look first at the XML file. Here we have John, who drinks a V60 coffee in the morning, a batch brew after lunch, and a flat white in the afternoon. If we were to represent this as a table, there are multiple options of how to do this. The first one in the top right corner of the slide violates the first normal form, because now the drinks column contains a list of things. So this is not good. And also it still misses the information saying when does the consumer drink which kind of coffee. Another thing we can do with the data when we would like to stick to the tabular data model is that we will introduce some redundancies. We'll add 2 more columns for the drink type and the time of day. But then we have the redundancies. So we so-called flattened the hierarchical structure into a tabular structure, which means that, for instance, the information that John is 20 is 3 times in the table. And so is the information that John drinks 2 coffees per day. So this is also not a good approach of how to represent this data in the tabular form. What actually would be the correct approach in a relational database, for instance, is to split this data into two tables. One would say that John is 20 and drinks 2 coffees per day, and another would say which drink is drank by whom and when. But then when we want to share this data, this would start getting complex as we would add more and more information. So actually here it starts to make sense to use a hierarchical data format such as XML. Because from all the options what we could do in the relational world to accommodate for this kind of data, none of those is optimal and none of those is as straightforward as the XML file on the left. So yeah, this is basically how I want you to think about which data model is appropriate for which kind of data. Another bad example, this one is from the real world, and actually this is how a Czech business register looks like at this moment. Is again on the left, you can see there is a piece of XML data, and from the first look, what would you think that the data is about? Well, you take a look at the element names and you see record, recorded header, and so on. So you would say basically that this is an XML file about some kind of records, which partially is true, but that is not how XML should be used. So you should not describe a data structure using XML, you should describe the data. So taking a second look at the data, what do you think the data should be about? Well, if we take a closer look, we see that those records are actually about companies which have headquarters and identifiers and so on. So if we were to represent this data as a proper XML, it would probably look something like this. So we would see that the data is about companies, and each company has an identifier, an address, and so on. So this is another example of how XML data should and should not be structured. Now, let's say that we have our XML data and we want to process it in an application. There are 2 or 3 basic or principal ways of how XML documents can be processed in applications. The first way is the most straightforward, and we'll call it the document object model, a DOM. And it works like this. It basically takes a look at the XML file and loads it entirely into memory. Then, when you have the XML file loaded into memory, you can of course query it arbitrarily. You can come up with any queries you want. You can walk through the XML tree in any way you want. This is also called a random access. So once you load the XML file into memory, you can do any random access you want. For instance, query it using XPath. We will talk about XPath, a query language for XML in the next lecture. What it doesn't allow you to do is you cannot process, for instance, streamed files like this. So if you would have a stream of XML elements coming from the network, for instance, or from some kind of a sensor, you cannot process it using DOM because you cannot load it into memory because you do not have access to the entire file at once. Another use case that is not well supported by DOM is when you have a huge XML file which doesn't fit into memory. Then you cannot use DOM. So for those use cases, there is SAX, Simple API for XML. It works in a stream fashion, which means that it reads the XML file as a stream of events, like start of an element, start of an element, start of an element, text node, end of an element, and so on. And it will generate, as it reads the file, it will generate events like these, and you will have in your code handlers for these events, and the parser, as it reads through the XML file, will call those handlers of yours, and it will push the events to your code. And it finishes when the whole file is read. Obviously, this works for streams. It works even for large files because the file is never loaded into memory as a whole. Of course, it doesn't allow you to query the file in an arbitrary fashion, at least not effectively. So here is an example of how the event stream can look like. And you can take a look at the XML file on the left, and we'll see element starts, consumers. So you'll see that the consumers element starts, and the SAX parser will call your handler of consumers element. Then element consumer starts, then element name starts, then there is a text value John, then element name ends, and element drinks starts, and element coffee type starts, there is an attribute, and there is a text value, then the coffee type element ends, and so on. And you can see that like this, it can go through a very large XML file and allow you to process it, but not in a random access way. There is another API for reading XML called Stacks, Streaming API for XML. And this works in a similar fashion to SAX. So it also reads the XML file as a stream of events. However, it doesn't push the events into your code. It allows your code to actually pull the events from the parser. So your code is in charge of when another piece of the XML file is being read and which elements, for instance, you are interested in that stream. One obvious advantage of this is that you in your code can stop processing the file when you are done with whatever you were doing with the file. You cannot do that with SAX because the SAX parser actually calls your code, and the SAX parser itself controls when it finishes, which is always when the file finishes. Right, so now we know how XML files look like, and we know how they can be processed in applications, at least in some principal ways. And now let's talk a bit about how actually XML can be used, for what it is usable. Well, there is a whole big set of so-called specific formats. You see, XML is sometimes called a meta format, and that is because it defines the syntax rules, but it doesn't talk about how the elements should be actually named and what they mean. So when you create a set of element names and their meanings and maybe some rules of how those elements can be nested, you are actually creating a specific format, specific XML format. And in that way, the XML itself is called a meta format or a host format. And what you created is a XML specific language. For instance, XHTML, where the XML elements are named as in HTML, and you have applications like web browsers which read that XML file and interpret it as HTML. So that is one of the many specific formats. Yeah, this is one way XML is used to define specific data formats. Then we already talked about how XML can be parsed. So there are standard APIs backed by specifications of how you can work with XML data. Then XML files can be validated. So given an XML document and an XML schema, you are able to say whether the document is valid or not, which is quite an important feature because when you receive an XML file and your application fails with it, you can always see whether the fault is in the document and therefore in the data producer or in your application, because you have the XML schema and the document needs to be valid against that schema. And there are multiple XML schema languages. 4 of them are well known. We already talked a bit about DTD, which we won't talk about anymore. And we will talk about XML schema in the rest of today's lecture. And there is also RelaxNG and Schematron, which are out of scope of this course, but they are also sometimes used to define XML schemas. And that's not all. There are standard languages for querying XML data. One of them is XPath, which we'll talk about next time. And the other one, which is kind of an extension of XPath, is called XQuery. we won't talk about that one in this course. And for transformation of files, there is XSLT, which we will talk about next time. And then there is a whole set of standards of how to represent XML in databases, or how to work with XML in relational databases. And then XML is used quite a lot in web services. So there is another big set of specifications on top of XML, specifying how web service messages should look like. And they are all XML based. So this is actually one of the most prominent differences between XML and JSON, which we will talk about some other time in this course. But JSON is also a hierarchical data format. And the main difference is that XML has a large ecosystem filled with standards that you can follow when building your applications. And JSON is simpler and doesn't have this ecosystem. That is why XML you will typically find in applications like banking, e-government, or enterprise systems, where there is focus on reliability and backing by the specifications. JSON, on the other hand, you will find in typical web-based applications where you basically do not need those specifications because you do not have a use case for those, for instance. So JSON is simpler, used on the web. XML is used in more serious applications. Now let's talk about XML and RDF. I already mentioned RDF XML as one of the standard RDF serializations. So let's take a look at how you can actually represent RDF, which is a graph-based data format or data model, in XML. So this is one of the specific XML formats because it allows us to use XML to represent an RDF graph. Now, why would we do that? You might ask. Well, RDF XML originates in 2004. Where many systems only knew XML and nothing else. So if someone wanted to send an RDF document, all they had was XML-enabled systems. So they devised a way of how to represent the RDF graph in the XML tree. The syntax, because we already talked about RDF Turtle, which is quite nice syntax. The RDF XML syntax is not that nice, and as you will see in a bit, and this might be the cause why in 2004 RDF was not very popular, because if someone talked about RDF, they basically shown a data format that looked like this, combining XML and combining which is a hierarchical data format with a graph-shaped data. So those were two a bit incompatible views on data, and the resulting serialization was not very human readable, which made it, or which was at least partially the reason it was quite unpopular before. So this is how an RDF XML document looks like, and this is one triple. There is the usual XML prologue, and then there is the RDF root element. There is definition of namespaces. Those are XML namespaces. However, they mean the same as RDF prefixes, and they are used as RDF prefixes throughout the document. And then each triple, or actually each RDF resource would be described by the RDF description element, where in RDF about attribute there would be the IRI of the resource, of the subject. So the description element says here we will describe a subject with the IRI in the RDF about attribute. And then was a list of elements. Those element names use the XML namespaces in the same way RDF prefixes work like. So here we have DC term subject, which we already know is a title of this thing. There is the language tag in the XML lang attribute, and the content of the element is the literal value. And then there is, so this would create a triple with a literal in the object position. And the second one is the typical RDF type, where the object is an IRI denoted by the RDF resource attribute. So this actually are two triples, one saying that index.html has a title in English, education, and the other one saying that the index.html is of a type 4th page. There is support for typed literals, so we can have the RDF data type attribute saying that the content of the XML element is of this type, which is an IRI of the data type. Alternatively, sometimes you may see the IRIs shortened by XML entities, which are defined in DTDs. This is just so when you see it, you know where to look for what it actually means. In RDF XML, we may have blank nodes where we still need blank node IDs. So for that, we may see the RDF node ID attribute used. And the only actual good use case for RDF XML nowadays is when, for some reason, your RDF literal would have to contain an XML document. In that case, you might specify the RDF parse type attribute as literal, which means that the content of this DC title element, for instance, is viewed as a literal value, is not processed as XML anymore, and is of a data type RDF XML literal. So if you, for some reason, need to insert XML file or XML tree into an RDF literal, then it might be advantageous to use the RDF XML serialization. Another example of a specific XML format is SVG, and you already used this one because this was a requirement for your homework, where I wanted you to have the conceptual data model in SVG, which is a vector graphics data format. And if you take a look inside the SVG file with your text editor, you will see an XML file with a specific elements and attributes. For instance, this triangle is represented by the XML part seen in the slide. And we will talk about SVG later in this course. Another specific format which you might have come across already without knowing it is the Office OpenXML format, which is used by Microsoft Office applications and other Office applications. So whenever you see a file with the .x or XLSX or PPTX extension, it is actually an XML format. It's not as simple as the other formats because it is actually a zipped container containing a directory structure and XML files. But if you write a simple document in Microsoft Word, for instance, this is what one of the XML documents inside that zip file would look like. So this is another example of a specific XML format. And yet another example, and our final example for today, is Atom or RSS, which is the format used for news feeds on the web. So if you use an RSS reader, for instance, and you subscribe for reception of news from some website, the feed you receive it in is an XML file. Actually, one fun fact is that RSS 0.9 and 1.0 and 1.1 versions were shortcut for RDF site summary, and they were used on an early draft of the RDF XML syntax. However, RSS 2.x is now a shortcut for really simple syndication, and it doesn't use RDF anymore, it uses just pure XML. I already mentioned that when you want to specify what elements can be used in an XML document and how the content should look like, you can use an XML schema language for that, and one of those languages is XML schema. This one is the most widely used, and we will talk about it in the rest of the lecture. Now, what we see here is an example of how an XML schema looks like. What you can see is that it is an XML document, So XML schema itself is an XML specific language. And what you can see there is a specification of a format of an address. You can see some sequence of elements and some attribute definitions. So this is really what XML schema is all about. It allows you to specify which elements and which attributes should be present in XML documents, compliant or valid against this schema, and how their content should look like. When you have an XML document and its XML schema, or sometimes called XSD, as in XML schema definition, you may link from the XML document instance to the XML schema so that applications can find the schema easily and can, for instance, validate the XML instance file. So on the top, we have the XML schema with some definition, which is not shown, and it is stored as schema2.xsd file. And on the bottom, we have an XML file instance, which has some root element, and in this root element, we have the XSI namespace defined and an attribute XSI no namespace schema location pointing to that XML schema. No namespace schema location means that the schema linked defines elements and attributes with no namespaces. When we'll talk about XML schemas a bit further, you'll see that an XML schema always says which XML namespace it targets. And then in the XML document instance, you'll have that you will use another attribute linking a specific XML schema for a specific XML namespace to this instance. Now, we already talked about the term well-formedness. We said that XML document is well-formed if it is syntactically correct. And now we'll define another term, which is validity. So an XML document is valid if and only if it validates against an XML schema. Now note that XML schema is with a lowercase s because that XML schema can be written in any of the XML schema languages. For instance, XML schema with a capital S, which is one of the XML schema languages. XML schema is again a set of W3C recommendations, so web standards. And there are again two versions, 1.0 and 1.1, and the situation is similar to the XML 1.0 and 1.1. When you work with certain tools, always make sure which versions of what they support. A lot of tools only work with XML Schema 1.0. Take a look whenever you choose a tool you will use for XML. And we'll start with something that we already have seen in RDF, and that is the XML schema simple types definitions. This document actually is the one which defines all the simple data types used throughout the data formats used on the web. So the XML schema 1.1 simple types are used in RDF, in JSON, in CSV, and of course in XML. So the whole tree of those types you can see in the slide, and the most common ones are booleans, URIs, dates, times, date times, date time stamp, which always contains a time zone, and the date time stamp is one of those types that was introduced in XML Schema 1.1. So if you are going to use it, this will allow you to see whether your software actually implements XML Schema 1.1 or not. Then there is the number types, decimal, integer, and double, and some data types for representations of binary files, because of course in an XML document you can have also a binary file included, but then it has to be encoded in a text, and that is done using either using the hex binary data type, where the binary file is encoded as hexadecimal numbers, or the base 64 binary, which is then another kind of encoding of binary files into text. And then there are some additional date types like G-year, which is used for representation of a Gregorian year, which is a regular year. So those are simple types, and there are many more, but we won't go into much details here because we already talked about and used those data types elsewhere. A fun fact, I mentioned that XML is often used in e-government. Well, if you do your taxes online, which you can do nowadays, you can log into that portal using e-identity, which is the Czech single sign-on implemented by the Czech government. And when you sign in, you are asked to verify that you really want to provide some details about yourself to the target service to which you are logging into. And the fun fact here is that if you take a look at the screenshot, it asks you as a regular citizen to verify your permanent residence provided in RUAN format. RUAN is the Registry of Addresses and other things in the Czech Republic. And it shows you this huge text, which is completely unreadable to common people. So this is quite funny. For those of you who will already know XML, you'll see at the first glance that it is actually a base 64 binary data type. And because XML is used in e-government, you will, of course, try to decode that string because you want to see what is being sent about you. And the result will be, again, an XML file that looks like in the slide on the right. So this is actually a common practice. I don't think it's a good one, but it is a common practice that if you are sending an XML message and you want to send an attachment, which may also be an XML message, you encode it using base 64 binary and put it into an XML element. So this is what is done quite commonly in e-government XML use cases. Right, so back to XML schema. The basic principles are, as I already mentioned many times, definitions of data types, both simple, which we have seen before, and complex ones, which we'll talk about in a moment, and usage of those types in elements or groups of elements and attributes or groups of attributes. And now we'll go through a set of examples where I will show you how XML schema can be used. So the most simple use case is that we want to specify the root element that can be used in an XML file. So on the top left, we have the XML schema. It is almost empty. It has just one element definition saying there will be a root element named catalog. Now, these element definitions in the root access schema element, they define global element definitions, which together form a list of possible root elements in compliant XML instances. In this case, there is just the catalog element allowed, which means that the green examples are valid and the red example is invalid. The red example is invalid because the root element in that XML document is catalog1, which is not catalog. Therefore, it is an invalid root element. And both of the green examples are valid because we only say in the schema that there is a root element called catalog, but we do not say anything about its content. Therefore, anything is allowed, and therefore both an empty root element and an element with some content is valid here. Now we'll extend the example and we'll add another possible root element, catalog1, into the schema, which makes both the examples valid, both with the root catalog element and the catalog1 element, because both are allowed in the XML schema. Right, so before we get to specifying the content of the elements, we'll iteratively reveal a decision diagram which will lead you to the proper XML schema construct that you want to use for specifying the content of the element. So the first question is whether your element, which content you want to specify, will contain sub-elements or attributes. If the answer is no, then you should use a simple type to represent the element or specify the element content. And the simple type is one of the simple types in the hierarchy that we have already seen, or it can be a restriction, which means that you take one of the simple types and you further restrict it. For instance, you can have a string which has only 10 characters, or something like that. Or it can be a list, which means that actually the value will be a list of values of some simple type. When XML schema specifies the list data type, then the list is separated by spaces. So you may have an element with a list of dates, for instance. And a union simple type is a data type consisting of a union of other types. So you may have a element content specified as a union of a date or a number. So both dates and numbers are valid content of such an element. Right, so let's take a look at the simple type definitions. So here we have the element catalog, and we say that its type can be Boolean. Therefore, only the instance with false value is valid. Empty is invalid because it's not a Boolean type, and nested XML element is also invalid because it's not a simple Boolean type. Now we'll restrict our simple type, so we'll have a base for the simple type integer, and we'll restrict it with the minimum value of that integer, which is 42. Therefore, a document instance which has a 42 as the content of the catalog element is valid, and 22 is invalid because it's less than the 42. So this is an example of how you can restrict a simple data type. So far, we used the element construct in the schema, and then within that element, we have defined the type that the element will have. But types and elements are separate in XML schema, or can be separate. So in this case, we actually define the type at the root element of the XML schema as a global type, which can be used then throughout the rest of the schema. For that, we need to name it. So here we create the simple type and name it at least 42. And then instead of defining the type within the catalog element, we just reference this type from the catalog element definition using the type attribute. So here the valid and invalid documents are the same, but the XML schema now uses a global type definition, which is then referenced from a global element definition. Now an example of the list. So here we have a list of numbers type, and we use it in the catalog element. And the valid is the list of numbers separated by spaces. And invalid is the second example where instead of the second number we have a text, which is not a number. So this one is invalid. And the union type combines multiple simple types together. So here we define a number or Boolean simple type and use it in the element. And therefore, both instances with numbers and Boolean values are valid documents. Another type of restriction which we may use with simple types is enumeration. So we may restrict the possible values of an element or attribute using enumeration like this. We enumerate the possible values. So, for instance, we enumerate 1, 3, and 5. So now, of course, the type name is nonsense, but what it shows is that 42 is not valid because it is not 1, 3, or 5, and 3 is valid because it is in the enumeration. Okay, so this was what we can do with simple types. Now, let's say that the answer to our questions, whether our element will have sub-elements or attributes, is yes. In that case, we need to do a complex type definition. And again, a decision awaits us. And the decision is whether this element will have sub-elements. And let's first take a look at what happens when the element has attributes but no sub-elements. In that case, we aim for a simple content definition. And a simple content can be either text content or, again, a simple type, but we can have attributes here. Right, so if we want simple content with attributes, we can do it like this. In the XML schema, we have the element, which now has a complex type, instead of simple type, and the complex type has simple content, and we extend a simple type with attributes. So we use extension here, and we extend the access string simple type, and we add attributes to it using the access attribute construct. For each attribute, we can again state its name, its type, and whether or not the use of that attribute is required on that element. So here, the first instance is invalid because it doesn't have the number of publishers attribute, which is defined as required. The other instance is valid because it has the number of publishers and its type is integer. So this is how we can define attributes for our elements. And this brings us back to our decision tree. So if we want both attributes and sub-elements, then we need to use a complex content definition with our complex type, and this allows us to specify which sub-elements are there in that element. So the first construct that we'll talk about regarding complex types is a sequence. A sequence says that there is a sequence of elements. It allows us to list those elements, again, by defining them as names and types and how many times they occur. The important thing here is that sequence is ordered. So the order of elements in that sequence needs to be the same in the instance as it is in the schema. So here we have a sequence of one element, and that one is called a data set, and it needs to occur at least once, but it can occur multiple times. So here the first document is invalid because it doesn't have a complex content, it has just a simple 22 number there. But the second document is valid because it has 4 dataset elements. One contains a text, one contains another element, one is empty, and the last one is also empty, but using the syntactic shortcut for an empty element tag. All those dataset elements are valid because we say nothing about the content of the dataset element. And the document as a whole is valid because the catalog element has a sequence of dataset elements inside, and those in this case are the 4 dataset elements. Now we'll extend the sequence with a data service element. So now in our catalog we want both datasets and data services. And the instance we have here is invalid. And why is that? Well, it is because as I mentioned, the order of elements in the sequence is important here. And the XML schema here defines that first one or many dataset elements come, and then a data service element may or may not be there. In the instance, there is a data service element, but after that, there is another dataset element, which is what breaks the schema or the validity, because after data service, there is no additional dataset allowed using the or within the schema. So if we remove the dataset at the end, we make the document again valid because it will again comply with the schema. Now, if we wanted the previous example to become valid with the dataset after the data service, we could make the sequence itself repeat by using the max occurs attribute and setting it to unbounded. However, like this, the document is still invalid, but now the reason is different. The reason is that the sequence defines the data service element with the default min occurs value of 1. And after the second data set, there is no second data service, and therefore it is invalid. We could make it valid like this. By introducing another data service element after the second dataset element. This now is valid because the document contains a repetition of 2 sequences, one after another, each starting with datasets followed by a data service. So this is technically valid. However, it is often not used like this, and it is a bad practice to mix those elements just like this, because it makes it hard to process such data. For instance, if you wanted to go through all the data sets, you have to skip those data services and so on. So this is not very practical. What is typically being done is that if you want to have multiple data sets and multiple data services in your catalog, and you want them to be repeatable or optional, what you can do is introduce a grouping XML element like this, data sets and data services, within which you have only elements of one type. So it makes it easier to process such a document. So the schema is on the left. Now the sequence is split into two sequences and into two elements. So now the catalog contains data sets and data services. Those elements are mandatory, and within those elements you have a sequence of data sets in data sets and data services in data services. And now the data services have min occurs of 0, so there do not have to be any data services within the data services element. So this is just a good practice of how to structure such XML documents. This is then the example of where we have no data services, and it is visible in the document explicitly because the data services element is empty. So it is better than the case where we had data sets and data services mixed together. Now, the sequence is not the only element content model that you may use. You may also use choice. The choice here says that the content is just one of the options specified. Not all of them, but just one. In this case, it means that the catalog element should contain either a dataset element or a data service element. So both the instances in the slide are valid here. And the third content model that you may use is the all sequence, which says that actually the sequence of elements is not ordered, which means that dataset and data service elements can or need to be present in the document, but they can be present in any order, which is a difference from sequence where they needed to be present in the prescribed order. So both instances here are valid, both the one where data service is first and the one where dataset is first. Now, elements may also be defined just by referencing a globally defined element which is defined before. So as we had global type definitions, which we could reference from an element definition using the type attribute, the same goes for the whole element definition. So here we have a global dataset element definition, and then we have a global catalog definition. This, of course, means that the instance may have a catalog and a dataset as a root XML element. But what is more important here is that inside the catalog definition, we say that there is a sequence of dataset elements, but those elements are not defined there. Just the definition just refers to the global element definition so that we don't have to repeat ourselves. And this allows us to reuse the element definition in many places of the XML schema. So either elements and types are defined globally, which means in the root access schema element, and then they can be reused throughout the schema, or they are defined locally within an element or type definition, and then they cannot be reused from other places of the schema. So in this case, the dataset element definition is reused. Now, I promised I'll talk about XML schema and namespaces. So up to now, we omitted namespaces in XML schema, so we basically didn't talk about them, and we assumed that the XML schemas define elements without any namespaces. But that is actually not the case most of the time. Most of the time, the XML schemas, the real-world XML schemas, say that what they define belongs to a specific namespace. And the namespace to which the defined elements and attributes belong is is denoted by the target namespace attribute on the XML schema. So here, the target namespace is http://npri.org, and all the definitions within the schema, in this case, fall into this namespace. Now, there is an attribute element form default, and its value is qualified. This relates to the qualified names I talked about when I was talking about XML namespaces. This says that each element defined is defined as qualified, which means that in the instance, it needs to be identified by its qualified name. So both the namespace identifier and the element name. The opposite of that is unqualified, which would mean that the elements defined in the schema do not belong to the target namespace of the schema. And then they can be used without the namespace prefix in the instances. The reason this attribute is on the schema element and it has the default is that like this, it is defined for all the elements in the schema. The alternative is that you can define the form for each defined element separately, which is of course lengthier because you need to repeat the form attribute on each element definition. So this means that the instance is the same. As you can see in the instance, the elements int A and int B use the namespace prefixes. One thing to note is that here in the instance you can see the XSI schema location. Before we have seen the no schema location, no namespace schema location, which was for XML schemas which do not use namespaces. And this is the variant where the XML schema targets the XML namespace. In that case, in the instance, in the XSI schema location attribute, we have a pair of values. The first is the targeted namespace IRI, and the second is the location of the XML schema file. So this is how you connect an XML schema using namespaces to an XML instance or XML document. And this is just to show you how a definition of an element with the unqualified form looks like and how it is then used in the XML document. So here int A has unqualified form, which means that it doesn't belong to any namespace, and therefore in the instance it is used without any namespace. So this was a very quick introduction to XML schema. We didn't cover all of the features, there are many more. For instance, you can have a schema split into multiple documents, and then the schemas can be imported into each other. We didn't talk about extending and restricting complex contents. We didn't talk about the any construct, which allows you to say that in this place of an XML instance, any XML is valid. We didn't talk about substitution groups, where you can say that in this in a specific place, different groups of attributes can be used. We didn't talk about mixed content, so how you specify that an element can have both text and sub-elements. We didn't talk about groups and attribute groups, and we didn't talk about integrity constraints. If you are interested in those, you are free to take a look at the specifications or find the information in some tutorial. Nevertheless, what we covered here will do for our purposes and for the homework.